And we're back. It's Dr. Jenkins. Here is video number 2 for our chapter on the general principles of nutrition. In the first video, we just got started, and now in the second video, we're going to be going through each nutrient, and we're going to be talking about its basic structure and function. So we already established that we have 6 nutrients. 4 of them are considered to be macronutrients, and you may remember that means that we need them, we need to ingest them in larger amounts. And then we have micronutrients, vitamins and minerals, that are just as important, but we don't need to ingest as many of them for them to carry out their function. You know, back in the good old days when we could actually meet on campus, one of the things I joke about with my students is I want to make little t-shirts. Maybe someday I will, although I haven't yet, is I want to make little t-shirts and I want to have written on them structure and function. Because that's the important thing. Those are the important things. So, in this chapter, again, we're just introducing these nutrients. We're going to go through each nutrient and we're going to talk about its basic structure and its basic function. I'm excited. So check it out. Here we have a nice summary table. This is what we're going to be going over. I like to provide information in many ways. Some people like a summary table, so this may be your jam. Other people prefer to study it slide by slide. But either way, I'm going to be giving you the most important information. So here we go. Let's start with carbohydrates. We already know that carbohydrates are considered to be a macronutrient, which means that we need to ingest them in larger amounts. You can see here I've got some information about what elements make them up, but that is something that you don't need to know. You can see I've also included a picture, and for each nutrient I am going to include a picture. I'm not going to ask you specifically about the picture on a quiz or an exam, but I do like to show you a picture just because it gives you an idea what it looks like. So, you know, if you were so interested, because science is cool, at what a glucose or a sugar molecule looks like, it's like a little stop sign. It's a hexagon with certain elements arranged around it. But again, not going to be on any quiz or an exam. What you do need to know, however, is the structure. So here we go. The structure of carbohydrates. We have simple sugars, and then we have complex sugars. A sugar is a carbohydrate, okay? So the simple sugars are either monosaccharides, and of course the prefix mono means one. So a monosaccharide is a 1 sugar molecule, and a disaccharide has 2 sugars. Di means 2. So you should know both of those. We have the simple sugars, both the monosaccharides that have 1 sugar and the disaccharides that have 2 sugars. And then we have the complex sugars, which are known as polysaccharides. Poly means many. So instead of it being a simple sugar, which is 1 or 2 sugars, here we have many sugars. Usually it's about 10 plus sugars. Look at this, nice and straightforward. So here are some other examples of what we just talked about. As we said, we have simple sugars, the monosaccharides and the disaccharides. The monosaccharides are just 1 sugar, disaccharides are 2. I'd like you to be able to give an example of each. So, one example of a monosaccharide is glucose. Glucose is our blood sugar. So when you hear someone talking about blood sugar, it's the amount of sugar in their blood. They're really talking about the amount of glucose in their blood, which is a monosaccharide. And then I'd like you to know as an example, sucrose. Sucrose is an example of a disaccharide. Sucrose is what we commonly know as table sugar. So if you're a coffee drinker and you add some sugar to it, that table sugar you're adding is sucrose, an example of a disaccharide. And then for our polysaccharides, which are many, many, many sugars, I actually would like you to know all three of these. So you should be able to identify that starch, fiber, and glycogen are all polysaccharides. Excellent. Now, I like, as best I can, to try to give some practical applications. I know to many people nutrition is not the most fun thing in the world. I know. But we see these types of sugars, these types of carbohydrates everywhere. I talked about glucose. That is our blood sugar. I talked about sucrose. That was one I asked you to know. It's table sugar. I didn't ask you to know fructose, so you don't have to know it for now. We will talk about this more when we get to our carbohydrates chapter. But just as an example, fructose is commonly found in fruit. Athletes eat a lot of fruit, right? And even in these GU energy gels that runners or other endurance athletes ingest, there's commonly fructose in there. See, so we do have these. Let's talk about these three polysaccharides. I would like you to know all three of these. Fiber, let's start with fiber and starch. Fiber, I'm sure you've heard of fiber. Fiber is a particular type of polysaccharide that helps us to move things through our GI tract. That's why it's helpful for particularly older people to help move things through. Fiber is found in things like cereal, frosted mini wheats. Nice and full of fiber to help things going through the digestive tract. And then starch, it's another polysaccharide. We know things that are starchy, potatoes, pasta. Athletes eat that too, right? And then lastly, let's talk about glycogen. Make sure you know the definition of glycogen. Glycogen is stored sugar. And let's just make sure we really understand this. So we have glucose, which we've already talked about, and now we're adding glycogen. Glucose is our monosaccharide, right? One sugar. And glucose is what's found in our blood. But now we're talking about glycogen. And I know they sound alike, so be careful. Glycogen is stored glucose, which is really the same thing as saying stored sugar. We tend to store glycogen or store large clumps of glucose in the liver and in the skeletal muscles. But it makes sense. Because here's what happens. Let's say as an athlete, I didn't mean to flip the screen there, I'm sorry. Let's say as an athlete, you have a big pasta dinner. That would taste good, right? Maybe the night before a big game, big pasta dinner. It's going to have a lot of carbohydrates in it. Well, after you eat that big pasta dinner, you don't need to keep all the sugar from that pasta in your bloodstream at once. It would just be too much. You don't need all that sugar in your bloodstream at once. So what happens is you eat the pasta dinner, your body breaks down the pasta into its smallest carbohydrate, which is glucose. We keep some glucose in the bloodstream, but then we store the other glucose as glycogen. Because again, we don't need all that glucose in our bloodstream at once. So after we break down into that big pasta dinner, we put some of that glucose into the blood, and then the rest we store for later. We store it in a storage form of sugar called glycogen. The other benefit of that is, well, after your pasta dinner, if you don't eat for a while, it's no big deal. Because if you haven't eaten for a while and you don't have any more immediate blood glucose, your body can just go to those glycogen stores and break them down, and boom, you have more immediate blood sugar, even without eating. Are you getting excited about what's to come? I'm getting excited. All right. Now, for each nutrient, we're going to be talking about a dietary recommendation. So, for example, on this slide, I'd like you to know this percentage. So, for carbohydrates, for most everybody, they need between 45 and 65% of their total daily caloric intake to come from carbs. Okay? So, for pretty much everybody, they need somewhere between 45 and 65% of their entire daily caloric intake to come from carbs. Know that range. And why is it a range? Well, people are different. Athletes, for example, are probably going to fall on the higher end of this because they need more energy. So they need more carbs. So maybe an athlete makes, on average, 62% of their diet come from carbs, versus someone who's sedentary, they need less carbs, or someone who's diabetic, they need less carbs. There's more information on here, but for right now, the only thing you need to know is that percentage for daily carbohydrate intake. All right, so we've discussed the structure of carbohydrates. Let's talk about the function. The only function I'm going to have you know right now for carbohydrates, energy. Carbohydrates serve as a great energy source for our cells. We have, a billion cells, millions, too many to count. And every one of those cells in your body, be it a muscle cell, a nerve cell, a skin cell, it needs fuel, it needs energy so it can keep doing what it needs to do. And one big energy source is carbohydrates. I want to make a point here. And I'd like you to know I would like you to know something a little bit more specific. And that is, carbohydrates are what our cells go to first. In other words, when your cell needs energy, its first choice of what nutrient to get that energy from is carbohydrates. What we're going to find out is we later burn a lot of fats for energy. But you see, fats are more difficult to burn down. So we can't burn down fats immediately. So we tend to rely on carbs first, and then as the duration goes on that we need energy, we tend to rely more on fats. But what I'm pointing out here is it's carbs that our muscles, all of our cells go to first. Now, truth be told, for pretty much any activity that we do, our cells are going to be using a carb-fat mixture. Okay, for any activity that we do, your cells are really going to be burning both carbs and fat. But it's just that in shorter duration, you're going to be utilizing more carbs. 100-meter sprint, you're going to be utilizing mostly carbs because it's what our body goes to first. But the longer that you exercise, the more time you have for your body to break down fat for energy, and the more fat you'll be using. But it's always a mixture of both. The rest of the functions here are all extra. You don't need to know them now. We'll be covering the other functions later when we get to our carbohydrates chapter. Let's talk about lipids. Ooh, fried chicken. Okay. So lipids is our second macronutrient. Most people tend to think of these as fats, but the appropriate term is actually lipids because it's a category that includes many different things. So you're going to hear me use the terminology of lipids, which includes many different types of fats. Let's start with those three types of fats or three classifications. One type of lipid is a triglyceride. This is what you think of as a fat. It's our dietary fat. It's the fat that's in that fried chicken. It's the fat that's in the Big Mac. Not that you would ever eat a Big Mac, though, right? But we also have two other types of lipids that we're going to talk about. Okay, so lipids is a category, and it includes 3 different types of fat: the triglycerides, or the dietary fat, and 2 others that we're going to be talking about shortly. In terms of the structure of fat, you don't need to know the ratio of elements. I've got some pictures here just so you can see that it looks different than the carbohydrate did. The top are the triglycerides. The bottom here is an example of a sterol. But again, I'm not going to ask you any specific questions about what they look like for now. Let's talk about these 3 different types of lipids. I mentioned the triglycerides are the dietary fats, the Big Mac fat. We also have something called phospholipids. And this type of fat makes up cell membranes. Everybody's familiar with the type of fats in the Big Mac, the triglycerides. But did you know that we have a different type of fat making up all of our cell membranes? Now you know. Let's take, for example, a nerve cell. I think most everyone here has seen a nerve cell before. It looks like a little kite. Well, if you were to look at that cell membrane, it in fact isn't just one boundary. And that's what they're showing you over here. Here's the outline of a cell. And if we magnify that cell membrane, it's actually 2 layers. And it's 2 layers of phospholipids. Each phospholipid looks like a little stick figure without the arms and legs. And what happens is that these phospholipids line themselves up into 2 layers. It's actually called a phospholipid bilayer. That's what we're seeing here, these little blue heads and then coming down, right? So we got this and this, this and this. If anybody is old like me and has played the board game Life, these phospholipids remind me of the little peg people that go inside the little plastic car. But pretty cool. So we have a different type of fat called phospholipids, and its job is to make up the cell membrane. Lastly, we have a 3rd type of lipid called sterols. And one example of a sterol is cholesterol. Also, our sex hormones, like testosterone and estrogen, are considered sterols. You don't have to know that now, but just be able to give an example of a sterol: cholesterol. Excellent. Now, what about the dietary intake? Again, we have a range. So for fats, somewhere between 20 and 35% of the total caloric intake should come from fats. That's all you need to know from this slide. And of course, we're beginning to make a list because we talked about carbohydrates. And remember, I know you're there waving your hand in the air. I remember, Dr. Jagans. Somewhere between 45 and 65% of all of our calories each day should come from carbs. And now we're adding that dietary fat. Somewhere between 20 and 35% of our daily caloric intake should come from those dietary fats. Excellent. Now I do want to make a point here. This is why it's going to be worthwhile for you to listen to these videos. When we get to the quizzes and the exams, the majority of the quiz and exam questions are straight recall. And it's straight recall from what we've talked about. So for example, I'm talking about these percentages. I'm writing them down, I'm circling them. So you could very well see a question on a quiz or an exam. What percentage of the diet should come from carbs? And you're going to choose the answer that says, oh yeah, between 45 and 65%. So it's all there for the taking. Yes, there's a lot of information that we're going to cover. That is the nature of a science course. But I'm giving you exactly what to study, okay? Now, the majority of questions will be recall. And then there'll be a smaller number of questions where I am going to ask you to do some critical thinking. But if you hit a home run, or at least a triple, when it comes to these straight recall questions on the exam or quiz, you're going to put yourself in a really good position. All right. I've already talked about excuse me there. Maybe by the end of this semester, I'll learn how to use this program. Okay. So functions, we talked about the basic structure, which is just really to say, know the 3 different types of lipids. Let's talk about functions. I've already talked about phospholipids. Their function is to form our cell membrane. Let's now add in our function for the dietary fats, or the triglycerides. And it is energy. But if I make it a little more specific, and I'm writing it down so you need to know it, what our cells go to second. So remember, what our cells go to first are carbohydrates. They're the quickest way for our cells to get energy. Fats take a little bit longer to break down and metabolize. So it's what our cells go to second. And remember, we ultimately end up using both. So your cells are going to be burning a carb-fat mixture. But if we were to talk about activity, anything that's really quick, you'd be using more carbs. Anything that's longer in duration, you'd be using more fat. Now, the triglycerides also help to insulate and protect our body. You got a layer of fat underneath your skin. Insulation, protection. You've got a thin layer of fat around your organs. Protection. And again, just know that cholesterol is a type of sterol, but you don't need to know the functions for now. All right. Here we are with protein. So we've talked about macronutrients, carbohydrates. We've talked about the macronutrient lipids or fats. And now we're talking about the macronutrient protein. All right, so what about the structure of protein? Well, here's a case where I'm actually going to ask you to know a little bit more. And that is, protein includes the element of nitrogen. Carbs and fat do not. Okay, so just know, out of the macronutrients, which one contains nitrogen? Protein. Not carbs, not fat, not water. Protein only. And I'm bringing this up because it is precisely because of that nitrogen that makes protein a little bit more difficult to handle. We're going to find out later in this course, protein takes longer to break down. Protein sometimes can be more difficult to deal with in the body. The byproducts of protein breakdown are also difficult to get rid of. We do it, but it's a little bit more arduous, a little bit harder than caring for carbs and fat. And the main reason why it's harder for protein is because of that damn nitrogen. Okay. Structurally, you should know that proteins are made up of amino acids. There are 20 total amino acids. So all of our proteins are made up of some combination of the same 20 amino acids. By the way, you can see here I have the shorter chains maybe can be shorter, maybe only having 100 amino acids linked together. We can have longer formations of protein that can have up to 10,000 amino acids strung together. I'm not going to ask you that specifically, but just pointing it out. And by the way, the AA here is not for Alcoholics Anonymous. It's just shorthand for amino acids. Here are some pictures of different proteins. You do not have to know these for now. But as you can see, the pictures on the right, different types of protein can look very different. What I would like you to know are essential versus non-essential amino acids. So as we've already established, we have 20 total amino acids. Of those 20, we'll start down here. Of those 20 amino acids we have in our body, 11 of them are considered to be non-essential. And what that means is, it is not essential. We don't have to get through food. Now, in our food, you have a chicken breast. There are going to be some non-essential amino acids in the protein of the chicken breast. So we are going to ingest some non-essential amino acids. But what they're saying is, you don't have to get all of these through diet. We will, inevitably. But they're considered non-essential because it is not essential. We do not have to get these through diet. And the reason why is because our body can make these 11 non-essential amino acids. If I could highlight this as much as was possible in the world, that's what I would do. Our cells are little protein producing factories. It's pretty amazing. And the protein that our cells can make are only the non-essential amino acids. Because our body can make these amino acids, we don't necessarily have to get them through diet. On the other hand, the remaining 9 amino acids are considered to be essential because we must get them through our diet. Our body cannot make them. Our body cannot make these essential amino acids. Therefore, we have to get them through food. Know these definitions, know the numbers. There are 11 non-essential and there are 9 essential. On the right, I've listed the actual amino acids, but you do not need to know them. I just put them on there. If you want to sound smart with your friends, go ahead and use some of those terms. You'll definitely sound smart. Okay, you don't need to know this now. As we're going to talk about later in our protein chapter, there are some foods that are considered to be complete proteins. Whey protein tends to be a complete protein. And all that means is, when you eat that whey protein, it contains all 9 of the essential amino acids. But you don't need to know that for now. Don't worry about it. What I would like you to know is this information. And there I did it again. Figure it out here. I wanted to bring it up a little bit and then, okay. How much of your diet should come from protein? Somewhere around 10 to 35%. So again, let's review. We can summarize 3 of the macronutrients. We know that for carbs, somewhere between 45 and 65% of all of our calories each day should come from carbs. We know that dietary fat, somewhere between 20 and 35% of our daily calories should come from fat. And now we're adding protein, somewhere between 10 and 35%. Boom! Now, I do have a question for you. If we compare these numbers, why is it that our daily need for protein is less than carbs, and often, in many instances, it can be less than fat? Does that mean that protein isn't as important? Nah. Let's break it down for you. Protein is just as important as carbs and fat. Protein is just as important. But the reason why we may only need 10 to 35% of our diet from protein is because our cells make protein for us. as I just talked about. Remember those 11 non-essential amino acids? Our cells are little protein-producing factories. So because our cells make some protein for us, we just don't need as much through diet because we already have some coming from our body. Protein's not less important. I'm not a protein hater. It's very important that you know that. Protein's important. But if we understand the science, our body makes a lot of protein for us. So because our body makes a lot of that protein for us, we don't need as much through diet. Now, carbs and fat, can our cells just produce carbs and fat in the same way as protein? No. Our cells are not little carbohydrate producing factories. Our cells are not little fat producing factories. So because we don't make carbs and fat in our body, we must get it all through diet. Whereas protein, because our cells make some protein for us, we just don't need as much through diet. But protein is still just as important to the body. Excellent. Now, as a small side note, our cells can make carbohydrates, but they can only make carbohydrates from something else. So, for example, it's possible for a cell to take protein and convert it into carbs or fat. But what I was talking about is our cells cannot just make carbs and fat out of thin air, but our cells can make protein out of thin air. All right, now, when it comes to protein, I would like you to know this number also. For a sedentary person, that is someone who is not athletic, not active. Couch potato, right? For a sedentary person, they need about 0.8 grams of protein per kilogram of body weight. So it's just another way of looking at it. You could analyze someone's protein intake by looking to see what percentage of all their calories came from protein. It should be somewhere between 10 and 35%. Or you can actually calculate how many grams they ingest and compare it to what they need. So you can do this yourself. You can play along. Let's do orange, different color, mix things up. You can take 0.8 times your body weight in kilograms. Now, we have to convert our body weight from pounds to kilos or kilograms. So to do that, you would take your weight in pounds and you would divide by 2.2. That's going to give you your weight in kilograms. If I were to do this myself, and I don't mind sharing, I'm about 152 pounds. Divided by 2 is, I know it to be around 69 kilograms. But feel free to plug in your own weight in pounds, divide by 2.2 to get weight in kilograms. So then to finish the calculations, I would take 69, my weight in kilograms, times 0.8, and that would be how many grams of protein I need per day. I don't have a calculator in front of me, so I'm not sure exactly how much that is. Maybe somewhere around 58, I don't know. But you should know that number. For a sedentary person, they need 0.8 grams of protein per kilogram of body weight. Now you might be asking, well, what about an athlete? Wouldn't they need a little bit more protein? And the answer is yes. So I'm not going to ask you these numbers on an exam now. We'll talk about this more later. But we could say an athlete, instead of being 0.8 grams of protein per kilogram of body weight, maybe it's 1.2 grams. A really high-level weightlifter, it might be as high as 1.7 grams of protein per kilogram of body weight. The highest I would ever recommend someone, even the most Olympic level weightlifter, would be about 2 grams of protein per kilogram of body weight. So of course, athletes do need a little bit more protein, but I'm not going to ask you those numbers for now. All right, let's talk about functions of protein. Here's a little intro, but I want to get right to it. I've listed these functions in order because I think it's the easiest to understand. One important function of protein is that it gives structure to our body. Probably everyone knows that protein helps to repair and rebuild muscles. We have over 600 skeletal muscles in the human body, so we need quite a lot of protein to be able to rebuild and repair and maintain our skeletal muscles. But it doesn't end there. Protein is also needed for structure, to give structure to our hair and nails. And I can't believe I forgot to put this on there, but also skin. The skin is our largest organ, covers our whole body. And our skin cells are chock full of protein for structure and protection. As athletes, shouldn't we care about ligaments and tendons? Of course. Guess what they're made up of? Protein. A second function of protein is that protein helps to form many important chemicals in the body. This is one that maybe people don't know as much about. Think about pretty much any important chemical in your body. Enzymes, hormones, neurotransmitters, antibodies, hemoglobin. These are all made up of protein. It's a different way to put protein together than, say, the protein for our muscles. But chemically speaking, these chemicals are still made up of tiny little proteins. So we need proteins for that too. And then last, we only burn a small amount of protein for energy. We only burn a small amount of protein for energy. We want to use the most of our protein for structure and to help form chemicals. Typically, only 10 to 15% of all of our energy to our cells comes from protein. And what that means is between 85 and 90% of all of our energy is coming from carbs and fats. Only a small amount of protein. You don't need to know this number for now. I just put it in there. But you should know that we only use protein for small amounts of energy. We don't want to burn large amounts of protein for energy because that means we're taking protein away from protein's ability to give structure and form chemicals. And it can actually have negative effects. Here are some pictures just to show you that protein and its functions. I'm not going to ask you this information or the pictures specifically. Here are some chemicals and how they're made up of protein. You don't need to know these specific chemicals. Just know as a whole, one function of protein is to help form chemicals within our body. Okay, let's talk about our fourth macronutrient. We talked about carbohydrates, we talked about fat, we talked about protein. Our fourth macronutrient is water. We know we need water. Come on now, you know that. Water is made up of hydrogen and oxygen. I'm not going to ask you that, but you probably already know it. We are made up of quite a bit of water. So it might be easy to say our body is usually between 50 and 60% water. So if our body is between 50 and 60% water, we need a lot of it through our diet. You know this. We got to stay hydrated. I'm asking you right now to know 3 functions of water, because we're going to have a whole chapter later on it, but just to get things started, you need to know these top 3 functions of water. One of the things that water does in our body is it acts as a universal solvent. That means it lets things dissolve in it. That's really important. Water helps with protection. We have a layer of water around our brain, around our spinal cord. We've got some fluid, some water in between the layers that cover our heart to reduce friction. And we also need chemical reactions because many, many chemical reactions in the body require water. So for whatever chemical reaction it is, a lot of times it just needs water for it to take part. Of course, water does more, but these are the three we're going to start off with. Okay, so we've covered the macronutrients. Let's talk about the micronutrients. You remember, micronutrients are things that we need in smaller amounts through our diet. These are not any less important than the macronutrients. We just don't need as many through our diet for them to properly carry out their function inside the body. You might be happy to learn. We're going to keep this very general for now. Make sure you remember that the micronutrients are our vitamins and minerals. You do not need to know their specific function now, because we'll talk about it later. How I want to summarize the role of vitamins and minerals in our body is to say that these vitamins and minerals act as a supporting cast. In this analogy, the star of the show is the macronutrients. We need more of them. They're more prevalent. They're more in your face, carbs, fat, protein, water. But we also really need these vitamins and minerals, but they tend to be a little bit more supporting cast. They have important roles, but they tend to act more in support. I do have a note here that we do not directly use any vitamins or minerals for energy. What we're going to find out later is B vitamins are needed to help us burn carbs and fat for energy, but we do not directly metabolize vitamin B for energy. Suffice to say, these are the supporting cast. Okay. And again, here's a nice summary, same one as before. The 6 nutrients, their basic structure and function, and in many cases, for carbs, fat, and protein, I'd like you to know the percentage of diet recommendations. We're going to end here for video number 2. We've got one more video left for this chapter, so make sure you return for that video. See you soon.